Converse of Cauchy's theorem. Now first let's see what the Cauchy's theorem is. Suppose fz be any function which is analytic in a simply connected domain D, and let C be any closed contour in D, then integral over C fz dz is 0. This is what Cauchy's theorem says. But converse of this theorem need not be true. Let's have a look over that. There is a remark for you. We might expect a function fz to be analytic at a point z0 if integral over C fz dz is 0. Alright. Suppose you are having z0 as an interior point in this yellow colored contour C. So along this every simple closed contour C in which z0 is your interior point, and if fz be analytic at this point, then integral over fz dz is 0. Right? But unfortunately, this converse of Cauchy's theorem is not true. Why? Let's see that. For example, we are having a function 1 over z square, right? Integral over C, this 1 over z square dz is 0. Along every simple closed contour C having origin as an interior point. Remember this. Origin means your z0 is 0 here. But function is not analytic at the origin. Since this function integral over this function is 0, but we are saying that this function is not analytic at the origin because now the point z0 as 0 it is given. In Cauchy's theorem, if the function is analytic at z0, we say that this integral is 0. But here integral is 0, but the function is not analytic at that interior point. Suppose this is your yellow colored C closed contour and this is your interior point z0, that is origin. At origin z0 is 0. So let's have a look over this. Suppose if you have a function 1 by z, what we say about the analyticity? This function is not analytic at 0. Why? Because at 0 this function is not defined. Suppose if I am having 1 over z minus 1, then function is not analytic at 1. Suppose I am having z minus 2 also. Then what we say? The function is not analytic at z equal to 1 and z equal to 2. So let's get back over our function. Our function is given as 1 over z square. So this function is not analytic at origin. Simple. Then this integral 1 over z square dz equal to 0, when this integral will hold? For that we have to take multiply connected region, right? So first of all just write that this function 1 over z square is not analytic at the origin. So let's draw a multiply connected region for this to make the function analytic. Since the function is not analytic at 0, I am making one small circle having the very small radius, let's say r, which is a positive 1. I have drawn this circle so that function is analytic, then the function will be analytic between this pink colored circle and the outer closed contour. Now in this region function is analytic. At 0 function is not analytic. I have drawn a circle for that so that function will be analytic between this region, outside this pink circle and inside this closed contour C. This region, yellow shaded region, here the function is analytic. Now we apply the Cauchy's theorem for this region, that is, now we are applying a Cauchy's theorem for the multiply connected region. So now 1 holds for this multiply connected region. So 1 holds because now the function is analytic in the region between the closed contour C and the circle mod Z equal to R, where R is positive, which is contained in C. Now the orientation for C is like this, because there is inside one more circle, so I take this orientation to be opposite to that of C. Remembering the domain, so we apply by Cauchy's theorem for multiply connected region. Integral over C fz dz. We have to take the union mod z equal to R. Now this is equal to 0, because this integral is 0 for analyticity for fz, which implies integral over C fz dz. We don't use positive sign, we use a negative sign because we are having different orientations, and this is your mod z equal to R, fz dz is equal to 0, which further implies what is fz? 1 over z square dz. Taking this integral on the other side, this is then equal to mod z is equal to R 1 over z square. dz. Since this is a circle, we take this in the polar form. We put z is equal to r e the power iota theta, and then your dz is equal to r e the power iota theta into iota into d theta, right? And whenever you take your z to be in the polar form, we have to write the limits from 0 to 2 pi. 1 over r square e the power 2 iota theta into iota r e the power iota theta d theta. E the power iota theta get cancelled, so this is now equal to iota over r integral from 0 to 2 pi e the power minus iota theta. Taken this e the power iota theta in the numerator in the inverse form, which comes out to be 0 if you solve. Alright, now your Cauchy's theorem is applied for the multiply connected region. Next, there is an expected example on Cauchy's integral formula which we need to do, which is very important. If C is a closed contour around origin, here also your z0 is equal to 0 given. We have to prove that a the power n over n factorial whole square is equal to 1 over 2 by iota integral over C a the power n e the power az over n factorial z the power n plus 1 dz. And from this we have to deduce this thing, summation on an over n factorial whole square is equal to 1 over 2 pi integral from 0 to 2 pi e the power 2a cos theta d theta. How we have to prove this? We are just going to apply the Cauchy's integral formula. Alright, just looking over this, the power for zn plus 1, we have to take the nth derivative for fz and apply the Cauchy's integral formula. So let's do this. Solution. What is our fz? Fz will be C. Taking fz to be as e the power az, right? So let fz is equal to e the power az What is the nth derivative for fz? See, what is first derivative for fz? A the power az. The second derivative will be a square e the power az. So like so on, we get the nth derivative to be equal to a the power n e the power az. Now the point is given to be at the origin. So what is nth derivative at origin? This is a the power n only. Fine. Now let's apply our Cauchy's integral formula. What is the form for the Cauchy's integral formula? We know that this formula can be written as nth derivative at z0, which is equal to n factorial over 2 pi iota integral over c f of z over z minus z0 n plus 1 dz. So we just have to use this formula for our fz as e the power az. Now z0 is 0, so instead of nth derivative for fz at 0, we have to write a the power n. Just put z0 equal to 0 and write, putting the values, integral over c. What is fz? E the power az. Z minus z0 is 0, so this will be z the power n plus 1 dz. Alright, here also z0 is 0, so f nth derivative at 0 is a the power n, so I have written a the power n. Now taking this n factorial on the other side in the denominator, this is equal to 1 over 2 pi iota e the power az over z the power n plus 1. Got it? Just we have to multiply the same fraction a the power n by n factorial on both the sides to get the result. See, we need this result. So there is a square. So just we have to multiply the same fraction on both the sides. So multiply a the power n over n factorial on both the sides. We will get the desired result. A the power n over n factorial whole square is equal to 1 over 2 pi iota n factorial integral over c a the power n e the power az over z the power n plus 1 dz. Proved? The first part is proved. Now for the second part, we have to deduce the another thing. Now this result is true for all the values of n, where n is your natural number. So now we have to take the summation on both the sides. So this result is true for all the values of n take the summation on both the sides over n a the power n over n factorial whole square is equal to summation n going from 0 to infinity 1 over 2 pi iota, taking n factorial inside the integral, a the power n e the power az over n factorial z the power n plus 1 dz. The next step is taking this summation inside the integral 1 over 2 pi iota integral over c, summation going from 0 to infinity a the power n e the power az over n factorial z the power n plus 1 dz. What I'm going to do is now and taking z the power n with a the power az and taking the other z in the denominator for dz. So this is equal to 1 over 2 pi iota integral over c. The summation is from 0 to infinity, taking this a by z the power n over n factorial and taking the other z with dz in the denominator, and e the power a by z will be outside the summation because summation is on n. So e the power az can be taken outside this summation. So this is equal to 1 over 2 pi iota integral over c e the power az. Now, what is summation for a by z the power n over n factorial? Do you remember that summation for x the power n over n factorial is nothing but the exponential form, right? E the power x. So this will be e the power a by z. Good. Which is equal to 1 over 2 pi iota integral over c e raised to the power a outside z plus 1 by z dz over z. Now taking the z in the polar form, which is, let z is equal to e the power iota theta, dz will be iota e the power iota theta d theta. Putting the values here, integral will be now in the limit form 0 to 2 pi e raised to the power a e the power iota theta plus e the power minus iota theta into dz is iota e the power iota theta over e the power iota theta. E the power iota theta cancelled out, iota comes outside this and d theta remains here, cancelling this iota also. And also we know that what is cos theta? E the power iota theta plus e the power minus iota theta over 2. So we apply here the formula for cos theta in the exponential form. This will be 2a cos theta d theta. Clear? Let me write nicely. 2a cos theta. This we need to prove now. Okay, I will write the formula here for you. Cos of theta is equal to e the power iota theta plus e the power minus iota theta over 2. We know this. Just putting the cos theta over here. Here ends up the result. In the next video, I will be doing with you that is the Morera's theorem and some corollaries for that. And do subscribe for the latest videos. And if you need the real analysis course, then you can check the description box and have a look over that course. Thank you for watching this video. Goodbye.